and we are very happy to invite Professor Martin Veselsky to give us a talk on the hypothetic X boson is the mediator of nuclear force. And Martin was born in Slovakia in 1966, and he received his PhD from Commerce University in 1997. And during his PhD studies, he spent 1 year at each of the floral laboratory of nuclear reactions in Lubla, Russia, and the GFI in Darmstadt, Germany, and since 1996, he proceeded with his scientific work at the Institute of Physics of Slovak Academy of Science. And between 1999 and 2002, he spent 3 years as a postdoctoral fellow at the Cyclotron Institute of the Texas A&M University. And in 2012 and 2018, he stayed as a visiting professor at the Shanghai Institute of Applied Physics in Shanghai, China. And his research has concentrated on various aspects of nuclear reactions, such as production of exotic and superheavy nuclei via complete fusion reactions, production of neutron-rich nuclei using reactions of nucleon exchange, study of reaction mechanisms in the Fermi energy domain, study of multi-fragmentation and liquid gas crystallization in nuclear matter, and study of nuclear equation of state and central energy in relativistic nucleus collisions. From 2019, he continues with his research activities at the Institute of Experimental and Applied Physics of Czech Technical University in Prague. His recent work focuses on application of nuclear equations of state in physics of compact astrophysical objects. Let's welcome Martin.
Okay, thank you for introduction. And my today's today I would like to talk about the hypothetical 17 MeV boson and provide some possible explanation which would not go beyond standard model, but which somehow will address some phenomena of nuclear physics and QCD. Anyway, like this. This story started by a report from the colleagues from Atomic Institute in Debrecen in Hungary, and it was somehow surprising that they were using practically just a tandem accelerator at very low energies, and in the reaction of protons with beryllium-7, they report some kinematic correlation, which according to them can be interpreted as a signature of 17 MeV boson. This work was published in PRL and then later got also attention from Nature News and even and other scientific and even mainstream media, where it was somehow advertised as the signature of the fifth force and dark matter candidate. What was actually the observation? Observation was following that this decay, it was the decay of excited state of beryllium-8 at 18.15 MeV. This is very high excitation energy for nuclear physics, and instead of traditional internal transition by emission of gamma quanta, it's also quite probable the excitation through emission of electron-positron pairs. And for this, there is some theories based on quantum electrodynamics, which give you some prediction on the shape of this polar distribution of opposing angles for given multipolarity. In this case, it was N1 multipolarity of this decay. And you see here that somehow this description for this particular state, 18.15, according to the measurement, somehow derivates from this theory, the prediction, and this correlation is centered around 140 degrees folding angle can be interpreted as a signature that prior to emission of two electron-positron pair, the excitation energy is transformed first into bosonic particle, and estimated mass is around 17 MeV. Later, the same group presented further observation also for other light nuclei as such as helium-4 and carbon-12, and also for beryllium-8 observation at lower 1+ state, 17.64 MeV. Even if there is much less, signal was much weaker. However, since 2016, when the first report was published, there are some experimental independent groups which work on this topic, but for now there is no independent confirmation. There is just one report from the group from Hanoi, but it's not cannot be considered independent, because also the scientists from Atomci were participating. This is somehow surprising that it was not confirmed yet in similar low energy experiment, but on the other hand, actually also at our institute there is a group working on this topic, and I can tell you that it's not easy. There is a lot of there are a lot of issues with the background, and simply this group from Leverkusen, they were working on this for a long time, so it might be that such reports may eventually appear later. Also, there were some experiments at high energy in pion decay, which didn't confirm this observation. Concerning explanations, there is one explanation in terms of the dark matter particle proposed by Spain. Recently, there is one explanation quite exotic to me, as few quantum electron mesons in 1+1 dimension, and there is also whole explanation within nuclear physics, which I will now introduce. Important to take into account is the fact that all the experimental observations reported by original atomic group are related to highly excited states, which lie above proton separation energy. So practically it means that those states are unbound. And also from this might follow assumption that those are actually cluster states, cluster configuration held just by together for some time just by Coulomb barriers. And this might lead to some assumption that this effect is actually related to nuclear interaction at long distance. This is how spectrum of beryllium looks like. At low energy, there are just first of all, even the ground state is not stable. It's unstable towards the decay into 2 alpha. And first three states, or first two excited state 2+ and 4+, they show that this is practically perfect rotator, because in nuclear spectroscopy, the signature of nuclear rotator is at first 2+, and 4+, the ratio is around 3:1. So it means that this nucleus is something like a dumbbell formed from 2 alpha particles. Then some levels appear only up above the separation proton and neutron separation energy, and there it's also one can assume that this state could have a cluster structure. And of course, it's also maybe it is good to verify this somehow. And what we did was actually going back to quantum mechanics by solving Schrödinger equation. But to using that, we employed this called somehow in literature mediator method. These two gentlemen, they actually some years ago, as mathematicians, they just published some handbook of differential solutions of differential equations. Like mathematicians, they had absolutely no idea about this application. But the point is that these equations can be mapped on Schrödinger equation with some specific point of potential, and it would provide you analytic solution. It can be demonstrated very simply on hydrogen atoms that practically from this equation you immediately get the correct result. And of course what we are understanding is actually most probably the computer regulation with 3 clusters. So for this you need some further tricks. One of them is to use so-called Jacobi coordinates, which in two-body case it will is the transformation into center of mass system, and in 3 dimensions you reduce it to the two-body problem. And another trick to use are so-called hyperspherical coordinates, which means that your two-body problem you practically transform into one-body problem in 6-dimensional space. And for this case, the final equation looks very similar, but with some different coefficients. Here it's instead of L plus 1 is L plus 4, and here instead of 2 is 5. And if you go with Coulomb force, the shape is result is practically very similar. So this is some general form which kind of potential you can use in this case. Actually, this exponential you have to take just a particle term, approximate them by 1 plus 1, say 1 minus alpha 0 plus r and so on. So that's the downside, but generally this potential after such modification will give you this kind of result, which is an analytical result for the problem. So how to test this problem? We took actually the carbon 12 nucleus. Specifically, there is some recent measurement from 2014, I believe. From 2014, which is they were studying just three alpha decay channel, and these are the states which you see in this measurement. So we took practically those 4 states and plus ground state and the first 2 plus state. And this is the final result. We, of course, since we have spin orbit coupling, we need to make some assumption about spin. So practically, we took spin only S and T wave 0 and 1, and also empirically we used this kind of selection rule. That very similar selection rule also in atom of hydrogen, but this n is not the main quantum number of hydrogen. This n comes from a solution of this Nikiforov equation. So it's somehow different. I will later explain. Of course, the method we did was that we scanned some space of parameters, and this is the best parameter set. And we also, one of the parameters is to get some spin. We also need to work with some energy which will open you because the alpha have 0 spin, so which will open you the one pair in one alpha. So practically, this time it works. Okay, go back. Practically, you see that this spectrum can be using the analytical formula and can be explained with precision below 1 MeV, which is practically very, I would say, very unique result for the nuclear physics. There's some story about Richard Feynman that he said that he left nuclear physics because he was not able to calculate spectra even for lattice nuclei. So maybe he should have this formula.
Is this test by using the carbon type?
Yes, yes.
Oh,
So practically this one is the famous whole state. So it would, in this time, it would tell you that this whole state is really 3 alpha state.
So by using the type, we have got some universal parameters like the V0, A0. The parameter is universal for different nuclear.
Yes, possibly. Yes.
This measure is for up between alpha particle.
Yes, yes.
Okay, why you have spin orbiter term?
Because without this term, you cannot reproduce the spectrum. We tried first without this term, and it simply will give you totally different spectra. And what this term gives you, that if it sends you the states with high spin low enough, otherwise you would have
Sorry, I will maybe this means so you treated the 3 alpha.
yes, yes. It's for 3 alpha system.
Alpha 0 plus their new spin orbiter. I mean,
Yes, that's what I say, that you need some energy to open one pair.
Yes, yes. And another question here, you found out 2 plus, that's 2 positive characteristics, 2 plus.
Well, there is no parity, but yes, it's 2 plus. This is very simple. 2 plus, 3 minus, 1 minus, 4 plus. It's like for yes. You are.
And there also another kind of the 4 binary state, that 4 minus states. I mean, experiment.
Well, we went
That will also be.
with this experiment where they don't see it, so that state may have a different structure. Yeah, can I continue? With this, let's call it structure, we use it as a test, and now we want to address also original problem of beryllium-8. But okay, maybe some explanation concerning this. Does it go?
No. Yeah, continue.
Can I go on?
Yeah, yes.
Okay. This is this selection rule is sort of empirical, but one can when looking into corresponding these are the wave functions corresponding to the solution of mediator of Uvarov, and with this there is some simple form which is relative somehow corresponding to the old problem. You see that the main is the so-called generalized ladder polynomial, and this has some order, and this order means how many times it is crossing the 0, and maybe because it's a cluster problem, you cannot, your wave function cannot go down to to zero because the clusters cannot overlap. So you need some 0 points, and there are just 3 0 points, for example, for third order Lagrange polynomial. So you may have just n minus your angular momentum can go 0, 1, and 2, n minus 1. So that's some possible explanation. And now let's go to beryllium 8. Well, this is the structure about 16. Practically, we took the states which you see in reactions with proton and lithium, which may have this kind of structure we expect. And for this, practically using the same method as for carbon-12, we get this spectrum relative to this 1 plus state is 18.15, and this somehow proves that this state is actually a ground state of this configuration of this cluster configuration. So first assumption that this is a cluster state, I think it's more or less confirmed. So now the second problem is what happens in this cluster configuration. And there the assumption is that this boson could be mediator of nuclear force. So that's the first thing we took the relativistic mean theory, and instead of standard we use omega meson as a vector meson. Well, I have to mention that there were also some assumptions about the observation about the nature of this particle, and at the moment vector particle and scalar particles are both possible. So since this theory is formulated as theory with vector and scalar, so we treat it as the vector boson, and really we were able to get some good equation of state, but with quite low because the coupling scales with mass, so we got relatively low couplings. And of course, we have to correct incompatibilities. So, and this was also put in at the time we used only constraints from heavy ion reactions. So further, here what I'm showing here is some I call quantitative arguments why this indeed could be a mediator. If you look on this plot, there are two lines. The red line corresponds to relativistic mean theory, and this line corresponds to the blue line corresponds to some chiral perturbation theory. And in the case of RMS, we, as I showed before, we got coupling of about 0.24, which means that if we go from the level of nucleons to quarks, it means for the quark 0.08 would be the coupling, roughly, okay, just rough estimating first. And this, if we use equivalent of the so-called Goldberg-Treiman relation, this relation tells you that in the case of pion and nucleon that practically, even if the separately actual currents of both pion and nucleon are not conserved, but together they are conserved for partial conservation of actual current. We just say that what we see here is that the as this Rose-Thurman relation works for pion and nucleon, those Martin couplings. The same way, this 17 energy boson would work with the current quarks practically. And so you see that both theories practically meet at the same point, exactly at the mark of about 17 energy. So I would say that this, if anything, if nothing else, this could be worth further investigation. And now the question is what would be the mechanism of this force mediation, and here we somehow found that something like instanton liquid model exists. And this is theory which started from work of Hooke, and this instanton liquid model was developed by Shuriak. And one of the further signals that maybe it's work, it might be like this. Let's call it this here. This is from some further publication of Shuriak, which they show here that there is this model has something called zero because it practically means that there are quarks which can freely hop from instanton to instanton. And for this, these are the parameters in this model that the typical radius of instanton is about 1/3 of Fermi, and typical distance is 1 Fermi. And when taking those values, you get for the width of instantons about roughly 20 MeV. Practically, I went to some. Actually, this calculation is not in published journals, but I found some preprint, which is actually in Russian, where this was calculated. So really, the values can be from 13 to, let's say, 25 MeV. So it can be 17 as well. So what this would be? It could be like first excitation mode of this vacuum. Practically, you produce particle wholesale across this zero mode zone, which practically this interaction would like this, that it's quadrant to a pair hopping through instantons between clusters. Of course, this is just some phenomenological assumptions. I don't think there is some theory which would somehow deal this in detail. This one, okay. Oh yeah. And here, thank you. Here is the before I already at the beginning I already mentioned some situation with the experimental verification, but recently the work appeared from Dubna, where they were measuring the interaction of proton and deuterium with carbon and copper in their nuclear machine. Practically, these are proton or deuterium, and this is so-called internal target. It's just some wires, carbon and copper wires, and they actually report resonance in the gamma channel. They report resonance at 17 MeV. And for us, what is important is that this is unlike, for example, other experiment at CERN, which studied particle decay. These are again reactions with nuclei where we have cluster structure. So it seems that really this cluster structure plays a role in such nuclei. So I go back to this status of experimental verification. As mentioned, there is just one somehow record of configuration which cannot be considered as independent. At higher energies, especially in pion decay, this was not observed. There is also one experiment studying atomic physics, some atomic physics, but it was made with relatively heavy nucleus, where you don't expect cluster structure. And there is this claim from Dubna, where they see similar effect with light nuclei. So our explanation that it is not new physics, but it's effect related to interaction of nuclear clusters. And in this respect, maybe it would be we already discussed it by the others, maybe also some data from stars could be also in data from stars with some light nuclei like oxygen, maybe could be also studied for this effect. I think especially maybe peripheral origins, because the excitation energy is not so high. And finally, we also, I showed before this equation of state, so we tested them also with neutron star practically using the standard procedure. This is the Solomon-Oppenheim Volkov equations, and these are the this is the relativistic nuclear theory. And what we see actually in this case, we didn't go with only X17 as the mediator, but you can actually use both X17 and the omega meson. And practically, what we obtain is some mediator with some effective mass in between those two. So we have some trigon, and using this we I think we can this kind of equation we can reproduce all the constraints, including this T-Rex2 constraint, which is the constraint on neutron spin of 208 length. And also in the last figure, we we could confirm some practically all the constraints on especially not all the equations, but some of those constraints from gravitational wave observations with tidal, this is tidal deformability, and also the observations from there is no nicer, but also nicer would be like this, so it's practically covered, and also the maximum mass. So I think that well, as I say, I want today I want to present some alternative explanation of this effect, and I think that there are several good arguments for this case. So in conclusion, as I have mentioned, this is still matter of discussion, and we somehow look for explanation within nuclear physics, and specifically we consider cluster structure and the interaction between clusters as responsible for this effect. Also, in the process, we did some spectroscopic calculations for light nuclei, and proved especially that for beryllium 8 it's a cluster state. And I mentioned several quantitative arguments point towards QCD vacuum as represented by instanton liquid model, and where the experiment can be understood as quasi-particle excitation. This means that it's not particle in the high energy sense, but because in high energy now the popular belief is that if, for example, collide electron and positron, and from this center of mass energy, whatever can be produced. But in this case, for production, you need also, since it is excitation of a medium, you need also this medium. And the medium is only in light nuclei. And of course, we also work into nuclear astrophysics, and using this, we were able to construct some successful equations of state. Okay, so thank you for your attention.
Well, I have several questions. I don't know what you can say. The first thing, I do not understand what is the relation of the first part of your talk with the rest. That means you have calculated carbon 12,
yes,
the alpha system, then you applied to the beryllium 8,
yes,
where it was like beryllium 7 plus neutron or B27 proton. You got the spectrum, which was nice. What more do you need the spectrum? When you are talking
to prove to ourselves that really cluster structure plays a role there.
But this we know.
Well, it's better to prove.
Oh, so this is the first. Second, experimentally, this quasi-particle, they were talking about beryllium 8, carbon 12, but also about alpha particle. Alpha particle 17 MeV.
Yes.
Well, then we don't discuss it. So why do you think that this kind of cluster degree of freedom should play a role in this helium-4 experiment?
Actually, the state in helium-4 is about 20 MeV excitation, I believe it's 1 minus, one.
Plus is 0 plus.
Yeah. But and again, as I said at the beginning, well above the proton separation energy. So it means that it's unbound toward decay into protons.
But I understood that you said the existence of this structure at 17 MeV is related to the proximity of the threshold. This is true in carbon 12, which is high up. This is true in beryllium 8, which is also high up, about the threshold, but not in alpha particle. Alpha particle is 17 MeV with these high excitations very deeply below the below all.
That's what I say, that it was observed in the state with 20 MeV excitation.
But you do not calculate the plus and minus decay. No? So how can you speak about resonance in the X17 MeV?
What do you mean? You mean reaction of a proton with, let's say, in this case, helium-3, yeah?
For example, yes.
So I believe they see resonance in this state, and just in this resonance they see this enhancement of folding this bump in folding numbers. So it's related to this given state, which if I'm correct, is about 20 MeV. So, and of course, it's above the threshold of reaction proton plus.
So, what is this 17 MeV? Boson or resonance?
It's let's say it's something like phonon. It's excitation of the medium, and this medium would be this instanton medium QCD vacuum.
It is not a state of resonance or excitation at the beginning metal system, right?
It's excitation of the QCD vacuum as a medium. Generally, this model of instanton liquid, well, I'm not the expert, of course, is considered as an analogy to condensate matter physics. So you can think in this kind of terms.
Can we go back to the group experiment?
Yes.
So that's the boson and
Yes.
carbon, right?
Yes.
So they use so the left part, so they use see the gamma
Yes.
on the A. Yeah, so I'm curious, so because it's GD energy, right?
Yes.
So I don't know if they also analyze the pi zero distribution, because pi zero also is able to gamma. So I don't understand fully that. So why it's 17 and
Well, that's basically the physics are surprises. To measure just things which you know before, it doesn't make much sense. So, well, they record this, and it would be best to verify it. That's what I say, that it fits quite well to our explanation of the problem.
And this is dedicated for this 17.
No, that was unrelated.
Oh, okay.
And they just came up with this.
Okay. I should read this paper.
There is also second, there is also second resonance at 38 MeV. but in some, when they take all data together, it's not really so significant. But if it exists, it could be actually two particle, two hole excitation, because it's slightly more than twice the twice 17 and so slightly more than 34 maybe.
But in this energy, really actually very hot. So it's more exciting, but it can be distinguished very believe from the.
Well, they're actually, I know somehow some people from Lubna, and I'm quite happy for them that finally they have some interesting result of their own, because most of the time they just collaborate with CERN, and they have been criticized for this, that they need also their own result. So I'm actually quite happy for them.
So is it possible for star to measure this gamma?
It's very tiny. You don't have the power. Very tiny.
The model value of light. It means
It's probably after subtraction in the ground. So yeah.
In this energy is similar with the volume 8 and 70 energy.
Yes.
So the volume 8 70 energy usually it cannot be explained the Wissenschaft of total ground state. So that state is not a ground state.
No, it's not a ground state, yes. Because practically excitation state of this excitation energy of this excited state is transformed into the state of
The volume 8 is spectrum. So
yeah.
no, the experiment, the spectrum.
Yes.
Yeah, 70 so one part.
There are practically two one plus states, but they differ because this is isospin 0 and this is isospin 1. And they are also here, three plus. They are also states. And this explanation actually, all those states have also the same isospin. The best combination.
Okay.
Well, it's also, I'm actually quite surprised that you can really calculate some nuclear spectrum so simply.
Right, based on another thing, why you emphasize this is the related class structure?
Yeah.
That's unrelated.
Well, because to have interaction between clusters, first you need clusters. You need to be sure that it's a cluster state.
Okay. So if there are any excluded regional clusters?
Yes.
Also with so because they didn't see
They didn't see it in experiments, for example, this way, with this ytterbium, which is heavy in a nucleus, where you don't expect clusters, and they don't see such effect. But of course, if you go with carbon, you always have to consider clusters.
I think that this everything comes from non-linear interaction mediated by instants. If you have this kind of instant as an interaction mediated, then it might modify the spectrum finite you get if you have this exchange of incidents into the interactions.
Oh. Well, for now we consider it just as a mediator and as shown by this relativistic mean field practically. There is some redundancy in relativistic mean field theory that gives you only the ratio of mass and coupling. So when the mass goes down, also the coupling goes down.
Okay.
So practically you don't see such a thing.
All right. Okay.
You have an idea how we directly populate this supposed redundancy?
Well, first of all, the best way is to somehow confirm the initial experiment. But you mean to populate it as a particle? Well,
As a resonance, as you say.
as a resonance.
70 nanometer. For example,
If it's,
you not shed the light,
Yeah,
photons,
yeah.
should you see the response of the system to the photon?
Possibly if you shed this light on cluster nuclei. It would be a maybe interesting experiment for laser with given energy and expose it to carbon nucleus.
Because if we do not see excitation energy in the photon spectrum, then
but practically what you see is opposite effect in this Dubna experiment that it apparently decays into two photons. So also this should be possible. Yeah. But of course the problem is that in the laser experiment there will be huge background.
And that's the key there is the column, and you can surround the red one yielding to the gamma.
You mean this Dubna experiment?
Yes, environment.
Well, I have no idea. Probably you have to read this e-print. But I believe it's a standard procedure, error mixing.
It's probably just mixing it.
Yeah.
You just
Yeah.
the 8 hours. Another legitimate question, if the X17 in the state exists, it's possible to reproduce the using that's its model.
Well,
Because it's the top that particle you can reproduce using the program for the bar to the classes. That's very
my feeling is that if it may be produced in high energy experiment, it will undergo such a process like hadronization, so practically it will turn into pyron. Because this practically you can consider this boson as practically chirally restored, so it gets into real world, it will become pyron most possibly. But that's just speculation.
very interesting. And maybe we can check online.
线上的老师如果有问题可以直接提问。
in this new particle, everything is a multi-particle with minimal structure like one particle structure produced with communication. And if it's true, it means we can find some unity right algorithm for the power principle. And from that, unification is related to the physical eventual fluctuation for public charge. And so for mathematics, this argument is a kind of particular effect we with the kind of music it can make the unbalance the character chart the vacuum and then if we have an intentional condition like the magnetic field and it can make a curve, the charge static along the field. And but for the moment we didn't see the signal and we didn't see the environment, the unbalanced environment result from the music. So I think this is very important funding. It related to the music. This
well, this boson is actually neutral, so I don't. Well, I'm a bit spoiled, but I would say that there's no direct relation to chiral magnetic effects. But on the other hand, there is not excluded that there might be also such combination which would carry charge. There is also exchange channel of nuclear reaction.
Probably very look for a few other later experiments.
Yes.
Careful.
Yes.